So the filter design for RF system, I think you have any question from the even the first slide. I have presented one image or an image of one river. Basically, river that always gives us a pure water. It has one process and purify the water by its own by using the chemical process, physical process, and biological process. It also has a filtering. That's why that is the reason why I am presenting here that river image. So river basically have some filter in itself by nature. Okay, now we'll continue that our topic as electromagnetic spectrum. Basically, that all electromagnetic wave comes under electromagnetic wave spectrum in all our applications. In that, all applications, particularly as AC engineers, so we are trained to communicate audio, video, data. These all are our basic information. That is the reason why we have all EC people or electronics and communication. We are trying to send information. That information is audio, video, and data. That may be analog form or digital form, or in that the channel wise, wire or wireless. Basically, in any communication system, we have a transmitter, channel, and receiver. So we have to design all the three in any communication applications. So we have an electromagnetic spectrum with various applications. So this shows that electromagnetic spectrum, all our applications, basically from radio, TV transmission, internet, and also now today's technology like mobile technologies or wireless technologies. So all that, even satellite, we have some certain frequencies. So the electromagnetic spectrum, it starts from very low frequency to optical frequency. In that we have a RF and microwave frequencies, that is from 300 megahertz to 300 gigahertz. That is in the wavelength from centimeter to millimeter waves. So this PPT shows that we have various applications including that radio waves, microwave, and IR, ultraviolets, soft X-rays, hard X-rays, and gamma rays. And also we have applications in that lower scale, that is in that in terms of frequency as well as wavelength and energy. So all three are related: frequency, wavelength, energy. So we are always moving to the higher frequencies. That is today's requirement. That is one point we have to see. If you are designing any components or systems in the communication link, that means transmitter, channel, and the receiver. The channel may be a wire or wireless medium, but mostly you have to design transmitter and receiver, particularly the transmitter and receiver components. Maybe in the transmitter we have either audio or video source, then modulator, then amplifier, that will also always used. In the receiver also we start with, if it is wireless, we'll start with antenna. Then we have various stage of amplifiers, LNAs, low noise amplifiers, and also filter. So we'll come to the filter topic later on. That before that we will see the three fundamental parameters in the RF and microwave engineering. One is frequency, and wavelength and energy. So these all three are related, and frequency C, that is frequency wavelength relation, C equal to F lambda, and E equal to H nu. These are two important relations. When frequency increases, wavelength become very shorter. When frequency increases, energy also increases. So that is this point we should know. And then microwave. Microwave, basically it is electromagnetic energy, generally RF radio frequency, except light wave. So it is propagate from one point to another point with source if you transmit. So we are using it in the communication, long distance telephone signals, TV programs, computer information from Earth or even satellite. And then information, that is audio or video or data that may be transmitted with wireless or wire medium, modulated or unmodulated, analog or digital. So we have various technology that also is studied. So now also that the microwave, other than communication, we have other applications like industries, agriculture, medical, automobile, even sports. Nowadays we have more microwave and RF applications. And frequency range that starts from 300 megahertz to 300 gigahertz, and wavelength is 1 meter to 1 millimeter. And then this is a relation, lambda wavelength is C by F or SC by E. And then we have energy but no mass for electromagnetic wave. And the release radiation by interaction between magnetic and electric field. And then travel at the velocity of light, 33 lakhs kilometer per second. And then three phasic property of microwave. Microwave are generally RF, that is radio frequency or microwave. General name is RF, that is from 300 to 300 megahertz to 300 gigahertz. Three phasic properties of microwave. Microwave can pass through glass, paper, plastic, organic materials. And also that another one that also reflect. Certain material will pass through or transmit from one point to another point. Certain material or medium, it's reflecting back. And also that in certain materials completely absorb. So we have these three type of category. So while designing any RF component, particularly filter, we should know what frequency we are going to design a filter, what is application. So then we always bring these three properties. That is one, penetration or transmission through the medium. Another one is reflection, even if it have a reflector, like a reflector antenna, or is penetrate to certain medium or molecule sugar level that absorb. And this is a spectrum, electromagnetic spectrum. We have various frequencies from very low frequency, 3 kilohertz to 30 kilohertz, and then 30 kilohertz to 300 kilohertz, we have another range. Then medium frequency, 300 kilohertz to 3 megahertz. Then high frequency, 3 megahertz to 30 megahertz. And very high frequency, 30 megahertz to 300 megahertz. Then ultra high frequency from 300 megahertz to 3 gigahertz. Then 3 gigahertz to 30 gigahertz. In that, where we have various microwave band like L band, S band, C band, X band, and KU, K, and KA band. Then we have sub-millimeter waves. So like that, more than beyond 30 gigahertz, we have extremely high frequencies. So why I'm showing this spectrum is in RF design, the first point is frequency. Which frequency we are going to design? When we will take example of filter, if it is very low frequency, we will go with the LC or RC filter. That is resistor, capacitor, resistor, inductor filter. But same thing at the high frequency, particularly beyond 300 megahertz, it cannot work. So we look for some other component. We should know the reason why these lumped components, so-called lumped components, like are discrete components. That is resistor, inductor, capacitor that cannot be used at higher frequencies because of we have a transmission line problem. So the dimension whenever we have the wavelength and physical dimension become comparable, we have all the transmission line problem. That is simple resistor act like that exhibits some series inductor, or the inductor that exhibits some capacitance in between the coils. Capacitor even that capacitor lead that exhibits some series resistor and also inductance. So these all are the problem by choosing the component. So the another question immediately we'll have in all communication applications, we go for high frequencies. What is the reason we are going to higher frequencies? Even mobile application or wireless technology. Earlier we used 2.5G, 2G, 2.5G in mobile, particularly in mobile communication. 3G, then 4G. Now we are moving to 5G and also 6G communications. So earlier in these all communication, we used to send only audio, but nowadays not only audio. So we are trying to send all the three information in multiplexed way. That is audio, video, data in different form. Analog. Now everything moved into digital. So then these all are the applications for microwave, RF and microwave, telecom, point-to-point communications, cellular access technologies, phase sensing, spectroscopy, communication, radio astronomy, medical application, diagnostics, imaging. Like that, we have many applications for RF and microwave, radar communication, security, in that GPS, like that. But in the particularly in the communication, if you transmit the signal and then you'll receive it in the far away, far long distance, that will be added with noise. So to remove the noise, immediately you'll go for the filter. That is electrical filter. Generally, if you say filter, there are many meanings. Filter is a general word. There are mechanical filters. There are even in our home we are using water filter like that. Naturally we have reverse, but we have RO filters. So like that. But is here electrical filter. So electrical filter, particularly at high frequency, what are the design issues or challenges we have? So this one is it shows some mobile development from 1G, that is earlier the first generation to second, third, and up to 5G. So first generation we used very low data rate. The reason is I already asked one question: why have to go for higher frequencies? Even why how to move for 5G? Answer is bandwidth. So if you use very higher carrier frequencies, that exhibit more bandwidth. That is the reason why even 4G and 5G we are using three different kind of higher spectrum. So in the first generation, we have 2.4 kbps data rate. So data rate is low. So if you have more bandwidth, you will transmit more data. But that depends on the operating carrier frequencies. But in the network side, it all in the physical layer. No, even the networking, people know that various layers, 7 layers, are in the internet. Advanced technologies, we have various layers, but these all become a physical layer. Even today's is a carrier level design or physical layer. So that if you use higher frequencies, higher data can be used. So, but in the 1G, you're able to transmitted only 2.4 kbps. Then 2G, we have applications of SMS digital signals. But in the 1G and 2G and all, we used in 90s, then 2 Mbps in 2000 around. Then now we mostly are in the 4G, I think in the LTE, VO voice over LTE. That is also we are using most of our mobile phones. Data rate up to 100 to 1000 Mbps from high data rate. Now there are a lot of research is going on in fifth generation technologies. That is particularly IoT, Internet of Things, and massive broadband and smart city, VR, AR, another thing. So in that, so now we'll come to the filter topic. The filters, basically electrical filters. So filters, we have a three type. Or before that, I'll have one question. How do you classify the filters? What is filters? What are the types of filters? That you should know. Sir, all of you, please wait 1 minute. Yes, are you able to hear me now?
Yeah, yes, sir.
Yes, sir.
Are you also able to follow the slide change? Yes, sir. Are you able to see the slide change also?
Yes, sir.
Yes, sir.
Yes, okay, okay. We'll continue now.
Yes, sir. Yes, sir.
Yes, filter. We studied various filters, but yes, sir. Okay. So filters are we have based on frequency. We have low frequency filter, medium frequency filter, then high frequency filter. Then we have very high frequency filter. So every frequency or microwave filter or millimeter wave, how is filter is designed, or satellite applications, how do you design a filter? So like that, we have various. The first parameter is frequency. So based on the frequency and application, we'll choose the filter. But basically, the filter are classified as active and passive filter based on the signal, analog and digital filter. So we and also we know that even digital signal processing, we are studying only filter 3, FIR, IAR filter, impulse response filters. Based on the component used, RC, LC, crystal filter. So that, for example, passive filter, for example, we have a LC or RC type. Active filter, if it is op-amp based, if you give a bias, then it's active filter. Then based on the frequency, just now I discussed, there are a low frequency, high frequency, RF filter, IF filter, or in the other domain also, optical also, there are filters, optical filters. Nowadays, optical filters are designed based on optical fibers and delay lines. This comes under delay line filter or microwave filter. So filtering basically a signal processing. Even there are even people, those who are studied in 80s and all, they had analog signal processing in their syllabus. So now even we have in our syllabus today, we are teaching in particularly ECE, digital signal processing or advanced digital signal processing like that. So like that, based on frequencies, we have various applications. Then based on the design method, there may be a Butterworth filter, Chebyshev filter, or Bessel or Coyer. Like that, we are using some mathematical approximation. Is based on the mathematical approximation. We'll be using either Butterworth or Chebyshev. So your filter may be analog with the order. For example, third order analog Butterworth or Chebyshev, low frequency filter. So like that we classify, and also based on the application for radio or microwave or radar, or mobile communication or satellite space communication or cable TV, like that, even include many applications. Like that, we have filters. And also based on the characteristic. So filter also we classify based on the characteristic. That is electrical filter type, low pass filter, high pass filter, band pass filter, or band stop filter. So we classify the filter or which application. For example, I need a filter for 5G application. What is our frequency? So I want to design sub 6 gigahertz, say 3.5 gigahertz. So our frequency, once as the frequency is fixed, then we have to choose the component, which component will support that 3.5 gigahertz and particularly bandwidth and all other additional filter parameters. But we will choose that is either analog or digital. Basically, it is because of carrier level filter. You'll go with yes. So we have that filter may be low pass analog or designed with filter with. So like that we have various filters. And then this an example for analog filter and digital filter. Analog filter, this is one is pump based analog filter, and this is one that digital filter. So that the analog filter we will design with, if you have a RC component, that is even in the mathematical formulation, we will find the transfer function. For example, we take symbol RC, low pass filter. We'll take that low pass filter, then we'll find the transfer function by taking Laplace transform. Then I will convert into digital. We will use ADC, analog to digital converter. Then after digitization, there also will use filter. So that which domain we are processing, that is also important. So based on the application, which domain or what frequency you are going to design a filter, that is important. So this is a comparison. So the analog filter will be using components, particularly in mathematical analysis, we call it as zeros and poles. So you have to choose a particular filter. So particularly that I'm talking about that transfer function. Mathematically, you will analyze a filter from the transfer function, even it's an analog filter or digital filter. So in the transfer function, even particularly we take single low pass filter, series resistor, shunt capacitor. So in that low pass filter, you'll find the transfer function voltage applied in and voltage out, then based on the Laplace transformation. The Laplace transformation, that means we are converting to frequency domain, that is natural frequency domain, that has some real term plus frequency term, that is S is sigma plus j omega. So then if you convert the same RC filter into digital by using either impulse invariance or bilinear transformation technique, then we'll convert to digital, and then we'll do the filtering in the digital domain. So that all design or choosing the component is all depends on what is the frequency application, what is the nature of your input signal, whether analog or digital or modulated or unmodulated, bandwidth. So like that we'll choose the filter. So this shows the comparison. This is basically that passive and active filter. So passive filter symbol RC, same RC by AppAmp. We have a RC filter. And then this is the fundamental filter design. 1 by 2 FC is 1 by 2 by R1C1. But the first problem comes, well, the another question you should know while before designing the filter, why we didn't use the distributed or lumped resistor or inductor or capacitor RLC at microwave frequencies, particularly beyond 300 megahertz. The reason is, if you choose this, if frequency is higher, the component value will become very low. Like that, it is, for example, the frequency is in gigahertz. For example, I want to design at 1 gigahertz. So if frequency is 1 gigahertz, the resistance value or this product, or even instead of RC, you put LC. These RC or LC product should be 10 power minus 9. Or if it is a LC filter where frequency is 1 by frequency proportional to 1 by root 2 LC. So LC product should be lesser than 10 power minus 18. So your component should be lower than nanofarad or nano Henry. So if you still increase the frequency beyond 1 gigahertz, particularly all our application, mobile or radar or TV, nowadays all our application, most of the application in the UHF band, so the 300 megahertz to 3 gigahertz, and also we have UWB up to 10 gigahertz, and also now we'll talk about 5G, the 3 band, there's give 6 gigahertz or around 20 gigahertz band, or 30 gigahertz, around 30 or 60 gigahertz band. So even in beyond, you will go beyond 1 gigahertz, the inductor value or capacitor value will become, that goes lower than nano Henry for inductor or nanofarad for capacitor. So then designing these values, for example, I want to design at 3.5 gigahertz, I am trying to design LC filter. So at 3.5 gigahertz, your component value will become beyond 1 nanohenry and 1 nanofarad. So basically, what is an inductor? Inductor is basically a solenoid coil that is proportional by number of turns. That is, inductance basic formula is mu naught n square A by L. N is number of turns, A cross section of the inductor. In the denominator, we have length. So if you again reduce the component value, size of the component become very less. Then other way that will become comparable to the wavelength. So the inductor or capacitor design is the component become very small. And comparable to the wavelength, it will also be radiate or couple noise, and also gives interference to electromagnetic interference or component interference or crosstalk. So like that, many other problems will come. So that is the one reason the normal component cannot be used at microwave frequency, normal LC or RC filter. Another question is, why can you use op-amp based filter? So if we go with the op-amp filter, operational amplifier, IC based filter, all ICs, we have some clock frequencies. That is limited. That clock frequency is also limited, and that clock, the higher frequencies, that it should be supported by the IC. So, for example, if you take I want to design LC filter, low pass filter using op-amp at microwave frequencies. But in the op-amp, beyond 1 megahertz, that is gain crossover frequency of op-amp, that will be a problem. So that will not support. So normal LC filter will not work. Even op-amp based filter will not work at more than 300 megahertz. So now we'll go for RF, specialized RF and microwave filters. I think in this figure I am showing 4 different kind of microwave filter. The first one, RF filter, in the PCB based filter with a special connector, and in one lower one, this one, we have some relatively some IF filter, but beyond 1 gigahertz, some even more than 1 gigahertz, you have to use either this cavity type filter or these kind of filters, or if it is a IC filter. So these all are the filters we have to use for 5G applications. 5G or higher frequency, you will say that's frequency more than UHF frequencies, that is 300 megahertz, more than that 300 megahertz. Another one is, just like that, we cannot leave as a circuit. It is a simple RC or LC circuit, just like that we cannot leave it in the board or PCB. So we have to close it like this. So because of shielding and to avoid interference, because of that going to operate at higher frequencies. And also we have to use specialized connectors. That connector, every connector also should work on that operating frequency that will support that bandwidth. And even single pin, single hole and grounding, everywhere you have to take care while designing high frequency filters. So these I am showing that 4 different market that is available in the industry's applications that I am taking from the website, various company website that is I'm showing it here to understand the different type of filters. And this is another time. You'll see various type of filters. So now we will see what are the specification. If you design a filter, you should know what is the specification of the filter. Basically, till now we'll discuss that starts from what is the frequency of application, what is the type of filter, whether low pass or high pass filter, or band pass filter, or band stop filter, or whether it's analog or digital filter, active or passive. So like that we'll classify. But another next thing is what are the specification? Generally, even you look into the spec sheet of any component, that will provide number of parameters. So like that we have one parameter. First one cutoff frequency. It is a low pass, one cutoff frequency, but it starts from 0. And then it is a band pass. What from, for example, 869 megahertz to 893 megahertz. One frequency, one band used in the 3G. So like that, we have various bandwidth. Then what is a attenuation? Filter bed basically should not attenuate the signal more. So that later on we'll also characterize the parameter in terms of insertion loss. So we have a cutoff frequency, bandwidth, and attenuation. Delay, group delay is another important parameter. It's measure how the different component of a modulated signal. Basically, all the signal in practical communication, we will not transmit only carrier. We'll always transmit some information. Is basically a modulator, either analog modulator or digital modulator. In analog AM, FM, or generally any phase modulation or digital. Digitally, if you convert the signal baseband signal to the digital, then we'll modulate with either ASK or FSK or some PSK, QPSK. Nowadays, even people are using satellite receiver applications and cable TV applications. We are using QPSK, even 64 QAM, quadrature amplitude modulation. 64 QAM and also 256 QAM. These are the standards already available in practice. So that every component that also receive it or that support that. So group delay that related to modulated signal, basically in terms of these waves. Then insertion loss is how much. Another one is this filter, particularly analog filter. Another one point is I'll say one example in TTH application, direct to home example. In TTH, we are using 2 different band, C band and KU band. That is in the direct to home. We are receiving C band, particularly in cable TV, we are using C band, and another one, mostly we are using KU band 12 to 18 gigahertz for TTH. So our dish antenna that receive around 12 gigahertz, that is in the lower band from the downlink from the satellite, around 12 gigahertz, that will be converted into IF around 1 gigahertz. Then they will give it to the set-top box for all demodulation, and they will come into baseband and give it to the TV. But if I want to process it in the IF, or you say example, I want to filter at around 12 gigahertz. So we need a filter at 12 gigahertz. But basically that all signal, digital signal. So one thing is, if you want to again, we will convert into digital domain. Somebody may think that we will convert into digital domain, then filter it. But we have a problem with the ADC. So designing ADC at higher frequency also, that is analog to digital converter. Designing analog to digital converter is a complex process. So that's why in that most of the filtering or receiving we it in that the same IF band. That is your microwave band maybe in the 12 gigahertz that come back into the IF. Similarly, we are using some techniques in that mobile in all our microwave applications. So that if you insert a filter in between, that also gives a loss, that is insertion loss. Basically, we know that we mathematically based on S parameter, scattering parameter, will derive it. So then Q factor is another important design specification. One is frequency, bandwidth. Next is Q factor. What is the Q factor of the resonator or filter is very important. Physically, how much energy stored, physically you studied in the Q factor of RC circuit, LC circuit. What is Q factor of the filter is very important. How far you tune that particular space and satellite applications. We need very precise filter. For example, I am designing filter, band pass filter from 869 to 893, maybe 92 megahertz. Around 894 megahertz, 25 megahertz bandwidth, 869 megahertz to 894 megahertz. Bandwidth is 25 megahertz. So if you design that, so that also that is precisely you have a cutoff. I want to allow only 869 megahertz to 893, 894 megahertz. We should not allow even 894.5 megahertz. So like that. So we have to use the precise Q factor, or that is also very important. Another one is for narrow band applications. Even we'll have some. This is this example 25 megahertz, but there are also some narrow band applications at high frequency. Q factor is very important parameter. So next is selectivity. How do you select how the filter pass particular band and reject the other band. So that is also selectivity parameter. Another one is VSWR reflection. The reflection also may be there. We have to do the impedance matching. Even when we design a filter, the challenge is using impedance matching the filter. Sometimes filter itself we act like a impedance matching circuit, even though it doesn't require any filter in the receiver circuit. So impedance matching related term VSWR, these are all very important for this application. Then stability, other thing is, if you know high frequency, immediately that also heat up. Temperature also increase. If you work, that's why we are using microwave oven that works around 2.4 gigahertz. So temperature rise, that temperature is one major problem at more than 1 gigahertz. So even any application, either satellite or 5G application, whatever may be the application, so that the component should also that carry the temperature stability, that is some kind of heat sink, or how to maintain that particular temperature. So the change in temperature that shift the cutoff frequency, pass band. So these all are the problem. So then, so these all are the major parameters or specifications. What is the frequency? What is the bandwidth? What type of filter? And what type of signal available, either analog or digital? Whether the particular filter that will support. The addition to that, Q factor, selectivity, VSWR, that is impedance matching, temperature stability. These all are other. And other than that, in addition to that, we will see what is the ripple in the pass band or stop band attenuation. These all are the additional parameters. But these all are the main parameters. We'll look into that in addition to pass band, bandwidth, pass band attenuation, stop band attenuation, or insertion loss. We have. The next is we have these all are the filters. That is crystal filter, surface acoustic wave filter, ceramic filter, cavity filter, planar. Planar means nowadays microstrip. One kind is coplanar, or strip line or microstrip line filters. In waveguide even waveguide will make into a filter. So these all are different high frequency filters that will provide high Q and selectivity and also support bandwidth. So that is a based on that we have to use that. The crystal filter, you will be using quartz crystal that will have some resonant frequency. Even you will tune it by parallelly connecting capacitor, high Q, high of a quartz resonator. That is a requirement. So that is up to then range within megahertz range. That is a crystal filter. When Q factor is around 10,000, even 100,000, we have Q factor. Then crystal also, that crystal monolithic that form two resonator, then also acoustic and high Q factor that allow crystal filter have very steep band pass characteristics. So like that we have. Then this is one example for crystal filter that is around designed around megahertz. But even the crystal with parallelly we have chip capacitors, that is SMD capacitors with connected with SME connector, sub-miniature adapter connector. That connector, everything and grounding, everyone should support that particular frequency or bandwidth. It's another example for crystal filter. Next, one filter generally used in that RF and microwave frequencies is surface acoustic wave filter. So that is called a SAW filter. Is also that can be used application up to 3 gigahertz. Is convert electrical energy or that RF signal to acoustic or mechanical vibration on a piezoelectric material. Once the electrical energy is converted into acoustic wave, the wave travel across the surface and that material. That amplitude will also decay. Generally, like lithium niobate, lithium tantalate, quartz, these kind of materials are used. Then this filter, the selectivity starts from more than 1.5 gigahertz and up to 3 gigahertz, and limited to that applications. And this is one example for surface acoustic wave filter. And then ceramic filter is another one type of filter. Is characterized very low loss performance and extremely high compactness. They are suitable for both commercial and military applications. This is one example for completely shielded and mounted ceramic filter. Cavity filter is another one most widely used in that particular military applications, even in the mobile applications. Cavity, resonant cavity, like in the waveguide, like a waveguide resonator. So that do a crucial role in enhancing the performance and stability also. That is the main advantage. High Q, that is resonant frequency by bandwidth, so generally Q factor. So of wireless communication system, and also high signal selectivity and the noise suppression capabilities. Cavity filter can differentiate signal of different frequencies, reduce interference, and that ensure communication quality. It's an example for expand cavity filter. It is expand 8 to 12 gigahertz. We have most of the microwave applications. The laboratory, inside laboratory, is another cavity filter. But this, how do you tune it? That also tuning also done by adjusting the screws and that connecting path length. These all other things will adjust that. Then in applications such as mobile, base station, satellite communication, we'll use cavity filter. It can improve signal clarity and stability, that ensuring the reliable operation of the system. Therefore, RF engineers, communication system designer, they have to deep understanding of utilizing this cavity filter, particularly mobile military space applications. Cavity filter is key features that is typically made of metal, like waveguide, either a rectangular or cylindrical cavity, like that. So we have other geometric shape also available. So this, we have a precise mechanical design that control is required and shape that to ensure the accuracy and stability of resonant conditions. And then high Q factor and high quality conductive material also should be used, copper, aluminum, and also precisely arranged within cavity to form resonance structures. And then these, to design these conductors, need to be precisely adjusted according to physical application requirements, including shape, size, and spacing between the elements. And then cavity filter for mobile base station also we are using. Mobile base station cavity filter used to separate signal from different frequency band, ensuring signal clarity and stability. So they selectively transmit signal at specific frequencies while suppressing the interference from other frequencies. This is crucial for improving the signal reception efficiency and communication quality of mobile base stations. And also, this is used for military communication system. So for military system, cavity filter commonly used to prevent interference, particularly from to secure from that other enemy signal or away from that secure wireless communication. So this is identifying, filtering out the signal at specific frequencies and also safeguard the security and confidentiality of military communication. Additionally, they are also utilized to enhance anti-interference capability of wireless communication equipment, or particularly in the field. So next filter is planar microstrip filter. So nowadays most popular kind of area of research like a microstrip antenna or microstrip filter, low profile, low cost, and easily will design and fabricate. And also most of the people, even you will see most of the research papers nowadays, most of the paper, particularly 5G applications, they are designing these kind of planar or microstrip kind of filter with different layers, different tunability, and also different by adjusting different parameters. So then the planar filter manufactured 2D resonator or pattern. So it's depending on the filter topology. Planar filter offer high Q quality factor and reasonable approach to achieve this performance. And planar filter is similar to PCB, like you know that like a microstrip. So in PCB itself, with that combination of dielectric and metal. And then the width of the strip element or dielectric constant of the substrate and thickness to determine characteristic impedance. Changing the characteristic impedance, that also very important. So that in all the design, the high frequency design, characteristic impedance and impedance matching comes into picture. Whether will design at 50 ohm or 75 ohm, these all are very low impedance. In low frequency, we know we worked with very high impedance in kilo ohm range, but here it is very low impedance, generally 30 to 80 ohm, but in mostly 50 ohm for all RF and microwave applications, particularly video transmission, cable TV, television, we are using 75 ohm impedance. So these design also we that based on that 50 or 75 ohm. This is one image that shows that the cavity waveguide phase filter, the screws above this, we adjust the screw iris, or we will call it as iris, that we will put in the equivalent circuit of this. We want to analyze, we will create equivalent circuit of this by adjusting screw size and everything. We will change the microwave parameter equivalently when analyze. But all these things, another important thing is we need high frequency tools, software tools like ADS, Advanced Design System, or CST, or HFSS, or any other high frequency software also required. High frequency specialized software to design all these components. Then waveguide filter or RF filter that use hollow conductive metal structure that carry RF signal like a waveguide in the laboratory. in our lab, in all our engineering labs in final year, we'll be using expand-based microwave link. That also will create into a filter by designing and also fabricate. If you have a very good mechanical or you able to shape the metals, you able to design it. But only this the people are also, there is also more research paper available in that designing waveguide based filter in addition to the planar or microstrip filters. This waveguide filter uses a practical solution for microwave millimeter wave bandwidth. Is able to support bandwidth. Another application handle high power. There is another point. So till now we'll discuss only with frequency. But power also another term. We have to some application, particularly microwave applications, some industry other than communication. So it will be operate in some high microwave powers, particularly industrial microwave applications. So that also, and also transmitters, satellite transmitters. You have to transmit very high power, then only the satellite at geostationary orbit that will be able to receive, because of channel loss will be more. So power capability also another important parameter. This will handle waveguide based filter that will handle very high power. So now till now we discussed so far we discussed various fundamental parameters like what are the filters available, what are the basically various communication point of view, particularly microwave, electromagnetic spectrum and its applications. Then we will discuss about what are the various different kind of filters, what are the specifications, then particularly the microwave filters. Microwave filter means ceramic filter, cavity filter, planar filter or microstrip filter or waveguide based filter. So these are the specialized filter that is used for microwave frequency. Particularly, you process the signal even in the microwave domain itself. That is required. I already mentioned that because of the other way is processing is will convert into baseband or digital. The design challenge in AD is always there. That is another area. So that now I am showing one example of low pass filter design that is designed in our laboratory. So that even that is this is also available in maybe many of the web material. So this one of the laboratory experiment we used to give it to our PG students to design a fourth order Butterworth low pass filter to using LC network at 1.5 gigahertz. Because of 1.5 gigahertz frequency, we cannot use directly a LC component. You know, there are so many reasons, like a transmission line, component availability, many reasons, many high frequency reasons, we cannot use it. But we know the fundamental design, we'll design it in the low LC filter, then you'll convert into microstrip. That is people generally using this method. So the substrate used is FR4. That is FR means fire retardant. 4 is generally a PCB material with dielectric constant 4.2 and substrate height thickness 1.6 or 5 mm, cutoff frequency 1.5 gigahertz and impedance. Required impedance, we used stepped impedance technique. There is also many technique to design this high frequency filter. So we have low impedance, high impedance, that is chosen as 150 and 110 ohm. So in this method, first we will choose the pass band and stop band frequencies. Then we'll choose the stop band attenuation and then use Butterworth. So we are using low pass LC filter, mathematical polynomial is Butterworth. So we'll design it, then we'll convert into microstrip. That is a design method. So that there is a generally we have to derive this polynomial from the transfer function, then we will design it. But there are standard table available or a polynomial available for Butterworth filter. Choose based on the number of components here and order of the filter. Another parameter, order of the filter. So if we increase the order of the filter, we have a precise response, but at the same time that increase the size of the filter, sometime we cannot accommodate in the PCB or within the system. So these all are that one side is order, other side is number of components. This we have normalized parameters. So this is a normalized parameter means these parameters used to assume as 1 radian per second frequency, 1 ohm characteristic impedance. So then we will design it 1 ohm characteristic impedance and 1 radian per second frequency. Then it will convert into particular microwave frequencies. This is a combination fourth order. So we are using 2 inductor and 2 capacitor, and this is for matching impedance matching on both sides. And this is a normalized value. This is a microstrip converter design. Then we used ADS tool, advanced design system tool, to design that. So this both side, this side and this side for impedance matching to 50 ohm. This indicate a inductor in series, this one capacitor in parallel, and inductor in series, and another capacitor in parallel, then feed line. So this length and width, so you have to calculate from standard formulas like transmission line length can be calculated from this formula, and capacitor is calculated from this formula. And then these all are the calculated values for this design. That is your length is 6.5 mm, then another length 9.2 mm, that is L1, L2 is given here, and then L3 15 mm, then 3.8 mm. So this is, we also fabricated. So what we did is we designed a normal fourth order filter in a LC way, then we use Butterworth polynomial, get the component value, then it converted into microwave frequency, that is 1.5 gigahertz. Then we will design, and then we will fabricated the microstrip filter. So then this is a design schematic in ADS for filter. So that is available. If you are using any high frequency tools, you should know. Most of the people know that. Then this is a layout design, and this is a subtract or a design in that ADS. Is a simulated response. You'll get around 3 dB, around 1.4 gigahertz. This is a simulated output. This is the simulated response for S11, that is reflection coefficient at particular port 1, and then it's a measured result at 1.5 gigahertz, and then it's another measured S11 of measured result. It's a comparison with measured and simulated result for S11 and S21. This is S21 pass band. There is a low pass filter. We have a pass band response. So then we have another S11 response with that. Then so these all are the one example also I have. So till now we'll discuss that some fundamentals or basic of microwave, particularly why you have to go for microwave frequencies, RF and microwave frequencies, because of bandwidth requirement, and the other time is when we work at the microwave wavelength become very shorter, then physical component wavelength become comparable. These all are the issues. Then applications, then filters. What are the various type of filters? Starting from RCLC filter, we classify the filter based on either type of signal, analog or digital, or active or passive, or based on the performance. And also we discuss about various specifications of filter, and also we discuss some parameters, some characteristics of various type of high frequency filter, particularly RF and microwave filter, say cavity or waveguide filter, that even design at say even 60 gigahertz. So like that another one is I have shown one example for microstrip filter. So this is about my presentation. So now have any questions? Over to Professor.